Let's look at a simple model for a battery, okay? Because there's this phenomenon. When you draw current from a real battery, the voltage actually drops across the terminal, okay? And when we say the terminal voltage, we're talking about just the voltage you'd measure if you put the voltmeter right on the terminals of the battery. Now, in our idealized circuits, our batteries have zero internal resistance, but the model is this, that this dotted blue line is sort of what we think of when we think of a cell, that it has some sort of electrolytic source of EMF, of voltage, right? But there's also always some sort of internal resistance, and it's this internal resistance that causes the voltage to drop at the terminals, and the terminals are here, between A and B. That would be the terminals, okay? So that's the phenomenon, and this is sort of our model for this, okay? Let's just look at this. Let's split this thing up, okay? So we've got this internal, this EMF provided by, the reaction between, carbon and zinc or something like that, right? Or lead acid or something like that. There's some chemical reaction going on, right, that causes a voltage, but there's also a resistance inherent in that battery. And the better the battery, and the better shape it's in, the lower the resistance, okay? So a good battery, a good cell, a good battery has a low internal resistance, low little r, right? And a battery that's all worn out, okay, a worn out battery has a high internal resistance. Internal resistance is not desirable, okay? Ultimately, you want a battery that provides almost any current about the same voltage, right? So we don't want internal resistance, okay? Now, if we take this formula here and we just sort of, bust it out, right? The EMF is just IR plus, and that's the external voltage on the external circuit, times IR, or plus I, little r, okay? So this is actually the external circuit voltage, right? That's the voltage across this guy, right? I times R, whatever this current is that's flowing through here. Okay, our current I, right? Okay, that is the external, okay? And then this is the drop across the internal resistance, okay? So there's two voltage drops. This one should be small. This one should be big, right? Okay, but because of this small voltage here, okay, the actual terminal voltage of the battery, if we just solve this for IR, the external circuit voltage, right, we get that the terminal voltage, and they don't have this formula, but it's a very useful concept, right, is actually that EMF minus the current times that internal resistance. That should make sense, right, that the voltage will be this, right, minus this IR. We could do it with Kirchhoff's laws, right, okay, that if the current's flowing this way, right, and we go this way through the circuit, it's going to be minus IR plus EMF, right, which would be this. All right, so let's just look at this. I want to just show you a graph of actual data, okay? So we've got this circuit here. The external circuit is attached, right? We've got this external resistor here, big R, okay? Well, the voltage across that external circuit is IR. So if I solve this for IR, again, right, I get IR minus or plus I times little r, right? If I solve it for IR, right, then the IR is just the EMF minus I times little r. I don't know what happened to my EMF there. I think it wanted to become something else, right? Okay, so we could say that the terminal voltage is the EMF of the cell minus the current times the internal resistance, like that. So if we actually measure this terminal voltage and graph it versus I, right, if we do a graph of terminal potential versus current drawn, okay, well, then we would expect, let's see, Y equals mx plus b, right, okay, V terminal is going to be negative R times I. I'm trying to write it in the same form, right? Okay, plus the EMF. Okay, so if you look at a graph of this, the slope of that graph is going to be negative R, right? And the y-intercept is going to be the EMF. Okay, so then here you can see the equation, right? So in this equation, you can see the graph, and notice that this graph is not we've exaggerated the y-axis, right? This only goes from 6.4 to 6.24, right? So it's sort of like a journalistic graph. We're emphasizing what's happening in the y direction. But when I put an equation through it, I get this slope there, right? I get that the slope is negative 1.3262, okay? That is negative 1.3262 is negative R, right? So therefore my internal resistance is 1.3262 ohms, okay? Now this is an alkaline battery that I got this data from. And what this means is that it's actually worn out, okay? Typically alkaline batteries have an internal resistance from about 0.1 ohms to about 0.9 ohms. The fact that this one is 1.3262 means that it's wearing out, okay? So as cells wear out, the internal resistance rises and rises, and eventually when you draw any current at all from it, the voltage will just drop and go away, okay? It's gone, okay? And so this is why you can't actually use a voltmeter to check a battery, because all batteries, even if they're worn out, will say, hey, look, I'm good, I've got 1.5 volts, and that's because you're drawing zero current from it, right? Remember, a voltmeter has an infinite resistance. So if you look at this, if the current is zero, even if that's like, something like 8 ohms or something totally unacceptable, 0 times 8 ohms is going to make this term just go away. It's not going to drop, okay? So the terminal voltage will just always read with a voltmeter, a good voltmeter, one that doesn't draw hardly any current, right? I mean, they have resistances of millions and millions of ohms, okay? A good voltmeter will draw zero current, therefore the terminal voltage will be essentially what the EMF of the cell is. So to test, a battery tester actually applies some realistic load to the battery, looks at how far the potential drops, does this calculation, and gives you that internal resistance. When they test car batteries, they have to hook it up to this scary thing with a fan, right? Because they'll draw 100 amps from the battery and see what the voltage drops to. That's how they test it. It's sort of like a stress test, like a treadmill or something like that, okay? Anyway, there you have it, right? This is a useful relationship. This is what's in the data packet, okay? I'm gonna bust out some examples here, and some of them we can use this. Some of them we have to have this idea, right? That the terminal voltage is just the EMF minus the voltage drop across the internal resistance. Okay, I'll show you how to do that in the next videos.